Hello. Today we're going to be talking about stars and this diagram that's in the reference table that shows us different types of stars, different temperatures, and different colors of stars. So, this is a picture of the sun. I don't think it's a real picture, but it's the general idea of the sun. We do have real pictures of the sun. Sorry I didn't show it to you, but you can Google it. It's pretty cool. It's a big fireball in the sky. But is it fire? No. It's not fire, it's fusion. So, stars are giant balls of gas, mostly hydrogen, and that hydrogen fuses together to create helium. And by fusing, it creates a tremendous amount of energy. So, the sun is not on fire. Fire is when we take oxygen, we combine it with some type of carbon or hydrocarbon, and it chemically bonds. Fusion is a nuclear combination of elements, and that releases insane temperatures. We're talking millions of degrees hot, crazy, crazy temperatures. And that's all about fusion. So fusion is what creates the energy inside of stars, and fusion is taking lighter elements or small elements and combining them to make heavier elements. So it's turning hydrogens into heliums. And it looks something like this. Two hydrogen atoms get squeezed under such high pressures and under such high temperatures that these two positive centers of their atoms end up connecting and creating a helium. So two hydrogens, or two deuteriums, if you want to be technical. You don't have to know that, but it's technically deuterium. Two hydrogens fuse together to make a helium. To get more complicated, right, there's a deuterium, there's a tritium. They fuse together to make helium. Just think of it as fusion is the energy inside of stars, and this releases a tremendous amount of energy. All right, two light elements combine to make one heavy element. Just give me a minute, please. So, this star diagram is going to be showing us different colors and different temperatures. So the average star is going to be around the middle here in this main sequence. So stars usually start as little red tiny stars, and as they grow older, they become more and more white. So our sun is about in this area. Our sun is a white star, and this is really going to be the difference between a supermassive star versus a regular sized star. So our sun is a regular sized star, so eventually we'll become something more like a red giant, and then the outer part of it will disappear and it will become a white dwarf. So the average sequence is it goes from main sequence to giant or supergiant and then becomes a white dwarf. Supermassive stars continue on this main sequence path, usually to become some type of blue giant or some type of super giant red star or white star. And those end up exploding and going supernova. But the main point behind this is that the red stars are colder stars. They're still really, really hot, but they're colder than blue stars. All right, blue stars have a lot of energy, so they're super hot. And then in the middle are these white stars, which have average temperatures. White and yellow stars have average temperatures. So just to give you some size understanding of these different objects, I believe the sun is one of these stars, and there are stars that are absolutely huge, and they're usually the red giants. They're absolutely huge. So we describe stars based on their color. The blue ones are really, really hot. The red ones aren't. The white ones are kind of in between. And there are super giant stars and there's little dwarf stars. But then there's this other term called luminosity, which describes the brightness of a star. So luminous or lumens are a description of how bright something is. So that's the connection we should make. The brightness of a star has to do with the size of the star. Supergiant stars are very, very bright. Really, really tiny stars are not very, very bright. But that has nothing to do with the color of the star. The color has to do with the temperature. Blue stars are super hot because they produce a lot of energy, which is short wavelength energy. Blue is a shorter wavelength. Long wavelength energy, which is red light, produces cold temperatures. Remember, not cold, but colder than the blue and white stars. All right? So, what we have here is the same thing that we have here. It's just that the colors are written down at the bottom, where all of these dots here are stars that are red on this side. All of these dots in the middle here are stars that are white. And then all these dots here are stars that are blue. This is a specific star called Spica. Spica is a supergiant, so it's really, really big. And it's on the blue side, so it's really, really hot. It's between 20 and 30,000 Kelvin hot. On the left side, we also have luminosity, right? So the small stars have a low luminosity, 0.001, 0.0001. And then the really, really bright stars, supergiant stars. They are 100 to 1 million times brighter than the sun. All right? So this is the diagram. So if I were to ask you, what star has a temperature closest to the sun? Well, we read down to temperature, right? So temperature that is similar is going to be Alpha Centauri and Polaris. A colder star than the sun, colder is on the right side, would be like Pollux, Aldebaran, Betelgeuse, Barnard star, Proxima b. A star that is hotter than the sun is going to be on the left side here, where we have the higher temperatures, Sirius, Eridani b, Spica. If we're asked about which star has its luminosity similar to Pollux, luminosity is on the left side here. So here's Pollux. I would say Sirius is very close. Aldebaran is kind of close. What star has a luminosity the same as Rigel? Betelgeuse would have the same as Rigel. Okay, so that's the main idea behind the stars and the star chart.